We have two equations to use when solving for velocity. The first one we should be quite comfortable with. It's our simple distance over time formula, where all we want to remember is that when we're solving distances, we want those distances to be in meters. And if we're given a time, we would want those times to be in seconds in order to get a velocity of meters per second. The other equation that we have to solve with is newer, and that's going to be velocity is frequency times wavelength. So frequency is measured in hertz or Hz's, and wavelengths are realistically still lengths, and so they are going to be measured in meters. And so when we do frequency and meters, we will get still meters per second, just as we always have for velocity. The other thing we want to recognize or remember when it comes to velocity is there's a few velocities that we know from our notes. And so we know that the velocity of sound in air is always going to be around 343 meters per second. And I say that it's around 343 meters per second because there's little things like temperature and humidity that can adjust the speed of sound. So sound needs a medium, meaning that when the temperature is a little hotter, all the air particles actually move a little bit faster and they carry that sound a little bit quicker. If it's super humid outside, then there's some extra water vapor which can help to carry that energy as well. So sound has a speed that we should always remember. And light, or all other electromagnetic waves, have a speed of 3e8. And a lot of times when we see the velocity for light or EM waves, they use the letter c to show that because it's a pretty constant speed. And that comes back to, in chemistry, you learned about E equals mc squared. Energy was mass times the speed of light squared. So c stands for the velocity or speed of light, but that also goes for all electromagnetic waves. So electromagnetic waves include things like radio waves, microwaves, infrared waves, ultraviolet waves, X-rays, and gamma rays, and then of course visible light would be in here. So you learned about the order of these in the notes from the previous week. I remember it using a little mnemonic. Red Martians invade Venus using X-ray guns, and that helps me kind of organize them. All of them have the same speed, but they do have different frequencies and wavelengths. So we're going to take a look at a couple of examples of that first equation. In our first one, we're asked how long means time, is the delay from the moment a lightning bolt is produced until a person 1 mile or 1,600 meters, we like meters, that's our distance, sees it. And so the other thing I'm going to pick out on here is lightning. Lightning is a version of light, so we're going to be able to use the speed of light, 3e8, as our velocity. So we have velocity, distance, and time. So we're going to use our old faithful equation, v equals d over t. We'll start plugging in the values that we know, and we're going to solve for time. So I'm going to isolate my t, so first I'm going to multiply by time on both sides in order to get rid of it. So now I have 3e8 times t equals 1,600. And if I want to get time by itself, now I'm going to divide by 3e8 on both sides in order to get my time. And I know some of you have been struggling with the scientific notation on your calculators. There's some really great free apps out there that you can download. Anything that has like a TI-84 style is what we've been using in class. But 3E8 really just means 3 with 8 zeros at the end. So I could also type it into my phone, just long form. And when I do that, I end up finding out that my time is 5.33 times 10 to the negative 6, or e negative 6. Or that might also be written as 5 zeros in front of that 5. So I've moved my decimal point over, essentially 6 spots in order to get that value. So those mean the same thing. Next up, we're going to look at our second part of the question, which wants to know how long, so this is still asking for time, is the delay until they hear the associated thunderclap. And so if I'm hearing something, well, now I'm talking about sound. And so my sound is going to travel at 343 meters per second. So I'm going to do the exact same equation, the exact same steps, but instead of 3e8, I'm going to use 343. Still going to use my 1600 meters because I'm still a mile away, and I'm going to solve for that time. And so the other way that we've solved this problem in class before is to think of this as essentially a proportion, 343 over 1. And so I'm going to cross multiply. But I end up with the same position. I end up where I have a number times time, and now I need to get that time by itself. So I'm going to divide. And so I'm going to see that I pretty much always have the distance on top, velocity on bottom. If I look back up at this one, I had the distance on top, velocity on bottom. So you also start to kind of recognize some of those patterns. And so when I do this, I'm going to get my time. So let's type this in the calculator and see what we get. It's a much bigger amount of time. Now it's going to take me 4.66 seconds in order to hear that thunder. So I'm going to see the lightning almost immediately, way less than a second, less than any of us are going to be able to make out. But it's going to take 4, almost 5 seconds to get to me in terms of hearing it. And so next we're going to take a quick look at the second equation, the other velocity equation. And for that, the first one that we have as our example is in music, a low C is 256 hertz. And so every musical note has a hertz. And if you have a tuning fork or if you have a tuning meter on your phone, it actually gives you that frequency. So that's going to be our frequency. And we want to know what is the wavelength. So that's that kind of upside down funky symbol, lambda, of a C played by an instrument. Well, if we're talking about music, if we're talking about playing a note, we're really talking about sound. And so we went over this a second ago. Sound has a speed of 343 meters per second. So even though they didn't tell it to us, I'm able to make an inference about what's going on. So in terms of my equation, velocity is frequency times wavelength. 343 is the velocity of sound, of a note. Our frequency for our low C is 256, and so we want to solve for the wavelength. So in order to get it by itself, I need to take that 256 and move it to the other side through division. So 343 divided by 256 gives us a wavelength of about 1.34 meters. And this actually comes into play as to like how long the instrument has to be. It's got to be some amount that will allow it to produce certain wavelengths of music. So different C's, low, medium, high, are going to be different amounts of that wavelength. So like half a wave, 3/4 of a wave, 1.5 waves. And so we can really get into a lot of musical things in terms of applications by understanding these relationships between frequency and wavelength. For our second example that we have down here, we have a gamma ray. Now if I remember, a gamma ray is a type of electromagnetic wave. So right off the bat, I know that I'm probably going to be able to use 3e8 as my velocity. And gamma rays have wavelengths of less than 1e to the negative 12th meters. Well, so that's going to be my wavelength. It's a meter, it's a distance. And the question is, how many gamma rays of that length would go through a person in a single second? So I want to know how many in a second. That's really the definition of frequency, how often something happens. So again, I'm going to use V equals frequency times wavelength. But this time my velocity is going to be an electromagnetic wave. 3 times 10 to the 8th. My frequency is what I'm solving for. And my wavelength is 1e to the negative 12th. And so again, this is scientific, which for some of you can give you some problems. So consider using an app. You're probably having to get some app type stuff going for your math class. The same calculator you're using there could be super beneficial here. And so just like before, I'm going to divide in order to get the frequency by itself. And so I'm going to divide by 1 times 10 to the negative 12th on each side. So 3e8 divided by 1e negative 12 is going to give me 3e20 as my frequency. So I would get 3 with 20 zeros after it passing through my body within 1 second if it was a gamma ray. Yeah. Some of this can even be done realistically with rules of exponents that you're learning in math, or that you've learned in math. So when you're dividing, you divide that whole number, and then we're really just subtracting these two. So it's like saying 8 minus a negative 12. Well, 8 minus negative 12 is 20. 3 divided by 1 is 3. So we can get creative with our math in terms of using some of those skills from your algebra classes as well. Since this is a frequency, I'm going to put hertz at the bottom to finish out my problem.